All right, believe it or not, we have a guest, it sounds like.
Wow. All right.
Which is awesome.
Yeah.
Great. All right, welcome to our guest, and I'll make it available later for people to watch so they can watch the discussion. So welcome to those people. I go by I Can Science That, but that's a mouthful. So you can call me Matt if you want.
Okay.
That's fine. And
the Rob or Rob, either one.
So this is our guest over there is Rob. Rob, why don't you introduce yourself?
Yeah, my name's Rob. I am a astronomy professor. I've been teaching astronomy physics for, I don't know, 15 some odd years. My career has been somewhat of a roller coaster in terms of the direction it's headed, but so I've done my fair share of research, but now I'm more interested in focusing on teaching, primarily from a small telescope avenue and also from science communication. So it's one of the reasons why I got into the flat Earth debate, as it were, was to essentially to explore avenues on how to better my ability to communicate using science. So,
wow, very cool, very cool. Yeah, we could talk about that really quick. My daughter is 12, and she asked me about getting a telescope. So I was really hoping she'd get into it. She'd really get into it, but I don't know, maybe her interest has sort of faded when I mentioned, yeah, let's get a telescope. As soon as I got excited about it, she's like, oh, wait, no, maybe I don't want
to. It's no longer cool.
Any recommendations on like how to approach a younger person who's maybe interested to really, to set that hook and get them interested?
So I would recommend something that is reliable and simple. So from my experience, because I actually used to sell telescopes at one point and another, one of the things I found is particularly when you start looking at the more, shall we say, cost-effective options, the mounting is such and the design is such that they're not easy to use. And so I found that people's patience quickly elapses if they don't have, or if they can't seem to be familiar with the equipment or can't seem to bring even the moon into focus. So what I typically, if you're really interested in trying to set that hook, what I would recommend is a small aperture, somewhere between 4 to 6 inch Dobsonian telescope, and that doesn't have a motor. Essentially, that's probably that is the least expensive, easiest to use, easiest to set up telescope. It's fairly lightweight. That would be the one I would recommend. You can use it. That one, with that sort of telescope, you can use it to look at things like the moon, the planets. You can use it to look at Albireo is a gorgeous binary star that you can look at. So pretty much all of the really big objects. You won't really be able to see, depending on your lighting and local lighting conditions, you really won't be able to see like a lot of galaxies or faint nebulae, but it's at least something that kind of drive home that interest. If they really like what they're looking at with the planets and the moon, then I think you can go the step further.
Okay, yeah, that's cool. Yeah, when I mentioned to her, we're in like the Los Angeles area, so light pollution is pretty bad, but we're close enough to the Angeles Mountains that you can drive up. You can drive up to like Mount Wilson, and they still have you can get far enough out and high and get some pretty good viewing, I think. So I talked about, yeah, we could do that at night, right? We'll go out at night and we'll set ourselves up a little tent, and you can, and she's like, oh, wait, stay up all night and it's going to be cold and I won't be using my cell phone the whole time. And,
I actually took my dissertation basically was in 2 parts. Half of it was taken using data from Mount Wilson. So I'm very familiar with that mountain.
Where are you located?
Right now I'm in Fairfax, Virginia.
That's why it's early, early for you. It's late. It's past midnight.
Yeah.
Okay.
Actually, have you been up there? Just driven up there up the Angeles Mountains at night, and it was one of my favorite things to do. Actually, was look down on the city,
Yeah.
because if you look
At
up
night,
stars at night, because the stars do not really twinkle, but the city lights do, because you're actually just slightly above that marine layer. So
the haze, the heat haze still coming off of the warm city streets and whatever, give you quite the shimmer.
Oh yeah, oh yeah.
Yeah. Yeah. I mean, I often think, circling back to the flat Earth conversation, you know, it's so easy to see these things. Like here in Pasadena, multiple times per year, at least once a year, usually not this year, but most years, the JPL will set up a thing. They'll set up a show, and the amateur astronomers will come out and set up their telescopes. And so you'll have 3 or 4 pretty big telescopes set up right in the city of Pasadena, and they'll look at Jupiter and Saturn and Venus and that sort of stuff, and just people in this public just come up and look. Everyone can come up and look at these things, and it's really amazing and really incredible. And I don't think any flat earthers do that. I don't think they know that you can just do that.
Yeah, I would be surprised if they did. I would be surprised if they did. And I don't. Obviously, I'm biased, but I think that there needs to be more advertising. I don't know how this would do it, but I'm surprised there isn't more word of mouth when it comes to, say, public events for astronomy, because I've moved around quite a bit, and so one of the things that I first do when I move into a new area is look for the local astronomy clubs, look for the public events that I'm not associated with, and that's actually not easy to do. It's not a resource that's quickly Googleable, if that's a word.
You can find it, but it takes effort. You're very right about that. And yeah, I guess that's sort of a double-edged sword, right? If it was more known, it'd be more popular, and then there'd be long lines to do these events. Probably the best one I ever got to do was Mauna Kea in the Big Island of Hawaii. We went out there on a vacation and scheduled ahead of time that it was the amateur group, but they have a fantastic group out there. Was setting up at the visitor center at Mauna Kea. So you drive up before sunset, you park, and then the sun sets, and they're setting up all their telescopes, and just tourists, can come and they share all of that. They're just so open about sharing out that with everybody because they're excited about it. They're excited to share.
Oh yeah. Yeah, Mauna Kea is definitely on my bucket list of observatories to visit.
Yeah, it was really fantastic. So it wasn't, the official Mauna Kea stuff. It was amateurs at the visitor center. But yeah, we could clearly see moons of Jupiter, the Great Spot and the stripes and all of that. You could clearly see those things. So yeah, the flat earthers, they show their videos of the out of focus stars, and it's just like, really, is that the best you've ever seen? Because
and they swear by, they talk about the Nikon 900, or I guess the Nikon 1000 or whatever it is now, as the premier observing instrument. I'm like, that's still a digital camera. You really need to use a telescope. You need a larger aperture.
Well, I don't have one. I don't have one of those myself, but it seems to me you ought to be able to focus it.
Yeah,
it should be focusable to. I mean, it's got a pretty decent lens on it, right? If you want a bright object, like you're just going to see a picture of Mars. Let's go take a picture of Mars. You ought to be able to image at least a circle.
It should be. Yeah, it should be a disk. I mean, I haven't really delved into. I think I've looked at people who are trying to image Venus, but again, one of the, kind of an aside, but one of the issues that I have with astrophotography from a flat earther is that they provide no details at all of what really they're using, other than maybe the camera, no time of day, no location, what have you. And so but I've seen quite a few videos on stars, and the issue they have is they're looking at a star that is twinkling, and they are making the assumption that the disk that they're seeing is actually the surface of the star, and that is in no way accurate. That is a combination of both the optics of the instrument they're using and the fact that the atmosphere is it's not steady state. It's not constant, and it's constantly causing the light to blur and shift and move and change color. So
yeah, absolutely. Yeah, I wonder. I don't have a P900 or a P1000 or whatever, so maybe one of the globe heads that has one could take it outside at night and take a properly focused photo of stars and the moon. And I have seen the moon. I've seen people do this with the moon, but maybe Venus. Can you see the phases of Venus with nothing more than a P900 if you simply focus it? I would like to know that.
Yeah, I don't know. You can certainly see it using an eyepiece with a reasonably well, actually you can see it with even a small, like I said, around, I think even with a 60 millimeter or a couple inch aperture telescope, you can see the if it's a crescent, you can easily see it as a crescent for Venus. But there again, you have to have the object or the telescope stable, and you have to have the telescope in focus. So, yeah, I don't know. One of the things that I've been lucky enough, I've always really had access to a reasonably good sized telescope. And so one of the things that I wanted to do or been thinking about doing on my channel is, either showing recorded videos or live streams of me taking CCD images of objects. However, the immediate response that the flat earth in the back of my head is like, oh, fake. It's an image. You're manipulating it. You're creating it. Whatever. Right. So I know that really shouldn't be a stumbling block, rather, but it's something that gets in my way when I try to do it.
Yeah, and let's transition to that. Let's transition to the discussion at hand, I suppose, which is relative density. And I think my take on that, my pitch on the relative density, kind of threw you for a loop. You seem pretty confused about what I was saying.
Well, the issue that I have, and I will fully admit to this, that I haven't really perused your library, your video library, and I do plan on doing that. So I was confused as to. I will admit that when I first saw your, I think, comment response about using that formula involving K,
Right.
I wasn't certain where you were on the sort of the spectrum. The impression that I got was that you weren't fully convinced that gravity existed, and that you were attempting to do your own independent path to essentially discover the truth, which I fully applaud. And so that's the framework from which I started with. So, but yeah, I like if you, so I'm assuming you are on the side that you believe gravity exists, and at least, with it is problematic, but so forth.
Right. So you're talking about this equation. I don't know if you can see.
Yeah, I can.
You can. Okay. I'm talking about this equation. That's my equation. And that's the one that, I put out there, and I call it the law of relative density. Okay. And the way, if you watch this particular video series that I did, I very much take the point of view from, the point of view is, hey, maybe gravity isn't real. Okay. Maybe it's not. Maybe relative density is a thing. Let's take it seriously. Let's treat it like a scientist is supposed to treat it, which is I have observations, I make a hypothesis, and I test it. where this, that's where this comes from, is people talk about relative density. It's all relative. It's all density. It's all relative density. And yeah, if you watch this series, the first video in that series is I was going to the kitchen with a kitchen scale and a measuring cup and some water and a rock, I think. No, I did ice. The first one was ice. So I measure some water, I measure some ice, we calculate the densities, we calculate the weight, we read the weight off the scale. And it's all supposed to be very, very doable, something that anybody can do, that just shows, hey, you know, density, weight, linear relationship, done, right? And I avoid saying things like linear relationship. I don't say that. I just say, you know, we weigh the things, we make hypotheses, and we learn. The first thing that we learned in the first video is that buoyancy does not cancel out the weight of the object. Right? Ice. The ice is floating in the thing, and we weigh. You weigh it, and you say, oh, hey, look, adding the ice, you know, we added 250 grams of ice, and sure enough, the thing weighs 250 grams more than it used to. And so the idea is we should be able to prove to anyone that the buoyancy of the ice doesn't mean the ice's weight is gone. The ice still has its weight.
No.
Right. And then so from there, then we go on a couple more videos, do similar types of experiments that anyone can do. And we develop this equation here,
Well,
matches our.
I want to, if I may interject, and oh, hi, dumb Jezza. I just figured out how to look at the comments. Was so again, not having watched the videos, if from a sleeping warrior perspective, and he is the one that has been has engaged me the most in explaining what RDD actually supposedly is from their perspective. He doesn't believe weight exists at all. So the idea that just putting the ice in there demonstrates that the weight has gone away or has been mitigated in some way, he's not going to accept that, because he doesn't believe that weight is a thing. It's relative density. And so the reason why reason why ice is suspended is because of the relative densities between the water and the ice.
Right.
You know, so I don't know how successful that would be. Well, that, you know, they're just going to
not very
consideration. So
not very. I'll be perfectly honest. Yes, Sleeping Warrior was who I had in mind at the very first when I made the very first video, because he does say things like weight doesn't exist, or I don't know what he says. He says lots of things. Let's just say.
Specifically, he doesn't believe that gravity is not a force. Gravity is not a force. That is his essentially quotation. What that specifically means, that is where he gets really squirrely. But that's what he's going to quote at you.
Yes, and so I had him very firmly in mind when I made that first video, and so I do not use the word gravity, except perhaps to introduce that we are going to question it. We are going to say that maybe it does not exist. Okay. And so we will not be using it. I did use weight. I didn't think he would object to the word weight. That was a misstep on my part, I think, because when you say weight, that's already a very charged, very loaded word that physics folks like yourself, you saw that word and you're like, no, that's wrong, right? And the flat Earth folks saw that word and their hackles got up and they're like, no, this guy's a glober. I'm not doing that.
Interesting.
So I thought that weight. See, the thing is, I took a kitchen scale, I put water on the scale, we measured it. What is that number? What is the number on the scale?
Yeah.
Is that not the weight? To a lay person, you would say, well, it's almost the weight, right? It's like it's
the mass.
And well, no, it's not the mass. I put it on a scale, not a balance, right? So So I measured.
Not sure how a digital balance actually accommodates for G, I guess.
It just assumes that G is 1.
Um,
So you can calibrate them.
wait, so if you have a digital scale and you put 1 kilogram weight on, or something that is a mass of 1 kilogram onto that scale, it's going to register 1 kilogram.
You need to calibrate them to get it perfect. But my kitchen scale, it doesn't even have a calibration mode, I don't think.
Yeah. So, but weight, again, from a physics standpoint, weight is the force pushing down on that scale. And so what the scale is actually reading is the normal force that it is applying in order to keep that plate at equilibrium. So
right. But then I use the word a little loosely. I refer to it through my first several videos. I referred to weight as literally the number on the scale.
Yeah.
The number on the scale is the weight. And you can see in this equation, there's a term that I think you will probably recognize as the buoyancy term.
Yeah.
Do you see the buoyant force in the equation?
Yeah, that would be it. Well, your sign convention is a little weird, but that would essentially be K rho m v naught.
Right, right. So the weight, according to most physics textbooks define the weight as gravity times mass.
Yes.
Mass times gravity is the definition of weight in many physics textbooks. But obviously,
actually, but yeah.
No, not all. Okay. There is a certain movement of which I am a part to stop doing that, to stop inventing words that are also in use by lay people and make them mean something different from what the lay people mean.
Interesting. Okay. All right.
Right. And so one of those is weight. Weight means something different to a physicist than it does to a layperson. To a layperson, you step on the scale and it shows you your weight.
Yeah.
You hang
technical jargon in a sense.
Yeah. Yeah. And the thing about that weight is it includes the buoyant term. The buoyant term is included in that one.
All right, I see where you're going with that. So, so I guess to be absolutely specific, what a scale is showing you is the apparent weight of an object. It is essentially, it is not the. So, again, I just want to clarify from a physics standpoint. As far as I know, I don't know whom you're referring to, but as far as I know, physicists and all physicists refer to weight as the mass times the gravitational acceleration of whatever you're at. 9.81 if you're at sea level, yada yada. Then you have, and so that is weight. Then you have the apparent weight of an object, which is what a scale reads. The scale is going to read what essentially is directly measuring the normal force, which is applied to, if we're talking about a digital balance or a digital scale, the normal force which is applied to the plate in order to keep it from sinking or rising or what have you, sinking really. And so that term encompasses a lot of different effects. It encompasses not only buoyant force, but you can also have different apparent weights based on the acceleration of the system. For example, if you're on an elevator and you're traveling down, if you stand on and anybody can do this, go into an elevator with a scale, stand on the scale, hit up. What you're going to find is that your apparent weight is larger as you go higher, and as you come back down, it will go further back down. So that not only takes into account, the buoyancy of force that acts on all objects because we are in a density gradient, but it also acts on, it also encompasses things like apparent weight. So,
yeah.
So I just wanted to be long-winded. I wanted to be clear about that.
Absolutely right. And you will not get any argument from me that is all correct. Where I'm coming from is a bit unique, though, and I'm coming from a place where I learned that, I know that, I accept that, but I am trying to communicate to people who do not have that education.
Okay.
And therefore, forcing them to use those words is, in my opinion, now this is opinion here, which is a significant part of the problem that creates flat earthers and other science, like we'll say science skeptics. I call them science deniers, but it's so negative. That I think I've resolved to say science skeptic maybe is a more friendly term. So yeah, I've got a paper here that is saying the same sort of thing that I am. The abstract is up there. That basically is saying, hey, maybe we shouldn't use this definition. We should instead use the operational definition of weight. And that's what you're calling the apparent weight, right? And all that means is the number on the scale, right? And so in whatever situation you're in, so if you're underwater and you got a scale underwater, that's counted. If you're accelerating, that counts. All that stuff.
One of the issues is, and this is really the key issue for me, is what are you going to do about units? Because if you're talking about a weight, because essentially now we're not only is it just a difference in terminology, but we're also talking about conflating a vector quantity with a scalar quantity. And not only that, just it kind of even goes beyond that, in that weight is a force. So when a physicist will refer to a weight, they're referring to a force. They're referring to something that is going to cause an acceleration. Whereas if you say that, this thing or this pen is 1 gram, that's not a weight, or that's not a force. That's a mass.
But isn't it though?
It will not cause an acceleration.
Isn't it though? What are your units for weight?
Newtons, typically.
Sure, but what is everyone else's units for weight?
Do you
have a bathroom scale? Do you have a scale in your bathroom?
Yes, I will. In layman's terms, everyone else's terminology for weight is grams, or is some kind of
grams, kilograms, pounds,
whatever. But I think that's a fairly important distinction to make, and I understand where you're coming from, and I agree. There is problems with terminology in terms of science. However, I think it might be going too far. It might be too far of a corrective issue to essentially abandon or redefine those things, because turning weight into all right, well, let me think about this for a moment. It's all right.
Well, let me suggest, as you think about it, take a closer look at the equation that I've presented.
Okay.
And you'll see that I did not turn density into a force. I multiplied by a constant.
You did, which is
which allows me to convert units.
Yes, and you also.
And if I had simply not called it K but called it G, you'd have not questioned it.
No, I would have. I think I would have.
Well, you still would have questioned it? Because
yeah.
That's the equation. That's our equation, right? That's the science equation.
Well, I think I would have, because K is, well, I may have questioned, because I don't know, because particularly if you had said it was equal to 1, I think that was the issue that I was having.
I did say that it was equal to 1.
And so you are refining it. The other issue, and again, maybe this is a semantic issue, but I don't think so, is that you have, not only is K a constant to which derives units, but you've made K a vector quantity.
Mm-hmm.
A vector quantity has meaning, and beyond just direction and amplitude, or magnitude and direction. I think it has a what's the word? More physical meaning to it, more causal relationship to it.
Yeah,
So if you're going to redefine weight as a non-force, then what would you?
no, I did not do that.
Okay.
What I'm doing in the first video where I introduced the equation, I don't show the vector arrows, and I do call it weight. I agree that calling it weight has. I thought that would make it easier. I thought that everyone knows that when you step on a scale, that's your weight, and so I was going to talk in those terms. But it was a complete flop. It triggered the physics folks. And it also triggered the flat Earth folks. So instead of trying to bring them together, which what I was trying to do, it didn't work at all. So I don't call it weight anymore. That is now the net force. So it is not. It is a unit of force. That is a force that is there.
I think I misspoke in that, because if you say that something is, so if I put this on a scale, according to this, and if it reads 1 gram, you're going to say that its net force is 1 gram.
Yes.
Is that accurate? Okay.
It's 1 gram of force.
1 gram of force. Okay. And so now you're going to make the distinction that if I were to say, want to look at the interaction of this rolling down an incline, looking at friction or rotation, then you're going to say that this has a 1 gram of mass and or 1 gram of
Yes,
it's M. Like that's where my stumbling block comes in is
right.
You know, when you're dealing with those sorts of equations, essentially, because my point of view is one would hope that people would take this sort of idea and then be able to expand on it to get to other areas of physics, because physics is a fundamental building block discipline. So it's more, I guess I'm thinking more a couple of steps ahead. So
yeah, exactly. I'm trying to take things very, very slowly. The idea was someone like Sleeping Warrior would, and honestly, I had him in mind for the very first video. I thought that he would watch it, and my hope was that he would say, yes, exactly. That he would say, that's what I've been trying to say. That isn't what he said. In fact, my first video, he didn't engage with it at all. He didn't acknowledge that it existed. It was Raichi. Raichi was the first person to seriously engage with it and say, hey, look at this. He's got an equation and he's talking about the right stuff, the stuff that I want to talk about. So she was the first one that really engaged with it. And Sleeping Warrior really does not want to engage with it at all. He just wants to shut it down in any way he can.
Yeah, Sleeping Warrior is not interested in debate or in discussion. He feels that essentially, I think the moment I lost complete hope in him was when he first told me that he did what Newton and Einstein could not, which was explain why objects fall. At that point, I was like, okay, I have encountered a very large spectrum of students. I have not encountered that before. So I do not know where to go with that. And because you get to the point, and this is something that a lot of flat earthers are accused of, and I really hesitate to go that far, is a lot of flat earthers are accused of being dishonest. I still don't want to say that Sleeping Warrior is dishonest, but I will say that he is not. His mind is not open at all.
No, not at all.
He will not even try to kind of work with an opposing idea. Like, oh, all right, if I accept that, then this follows from what you've just told me. He won't do that. He will just tell you you're wrong, insult you, and then move on. Maybe.
Right. Well, yeah. On Sleeping Warrior, the very first time I became aware of him was when he commented on a video that I had, one of my earliest videos that I did. And he came to comment to, and one of the things he did was he wanted to gloat that he had tricked me into debunking him. He had tricked me into debunking him. And I was like, I don't debunk, and you didn't trick me. I show the truth no matter what. You don't have to try to trick me to get me to show the truth. And what it was he had, now, according to him, like, I'm not trying to make out that he's a liar. According to him, he had deliberately falsified some evidence and presented it on one of their shows. Oh, wow. And I had picked up and debunked it. And he's like, haha, you fell for it. And I'm like, why would in what way is that honest? Either A, you were lying to your own viewers and telling them false evidence just to try to trick someone like me, or more likely, perhaps, I caught you in a mistake and you don't want to admit it, and so now you're lying about that. Either way, it's dishonest. But that said, let me give him the best defense that I can possibly offer. Okay. And that is, he comes at this like a lawyer. He does not come at this like a scientist. He comes at this like a lawyer. And so that means he will do nothing but defend his side. He will not offer you anything conciliatory at all. He will never give ground, because he thinks of it like a lawyer, where there are the two sides opposing. And I think you also see that he delves into the wording, and he tries to get into the wording to the exclusion of the meaning. The meaning is not important to him. It's the wording that's important to him. And yeah, you'll see that in all of his stuff. So
what's funny, and if I may interrupt for a moment,
go.
Funny is that it kind of goes to what you were saying at the very beginning, in that the difference between, and perhaps this is why you really you took the position that you did, that the definitions are really what are tripping up the flat Earth community, or at least certain proponents of the flat Earth community, is that they'll go to Merriam-Webster, Merriam's dictionary, and they'll say, weight is this, and so obviously gravity, it's weight is associated with gravity, so therefore weight doesn't exist, or what have you. But yeah, so yes, I fully agree that he takes definitions from wherever. He used to actually cite the dictionary he took them from, but he doesn't do it anymore. He takes those definitions and he treats them as gospel, without realizing that there is jargon in every field. There is jargon in physics, there's jargon in astronomy, there's jargon in computer science. I mean, a demon to a computer scientist means a whole lot, something completely different than it does to someone in the clergy. So, it's funny aside, there is a flat earther out there who actually does believe his computer works on demons using.
There probably is. I mean, there probably is.
But anyway,
yeah, I think I'll go you one further. I think that Sleeping Warrior knows that his semantic arguments and his definition cherry picking and so forth, I think it's deliberate. I think it's very much on purpose. But I think, again, from that lawyer point of view, I think he feels that it's appropriate to do that. I think that what he actually believes, I have no idea. I have no clue what's going on in his brain. Does he believe that the Earth is flat, or is he just trying to defraud people? I cannot tell. What I know for sure is that he is not presenting the whole truth in an honest and unbiased way, that he's deliberately skewing everything the best that he can.
I would definitely agree with that, and I'm with you in that I don't know what his true motivations are.
Right.
Like Nathan Oakley, I have my own strong opinions on what his motivations are. But
Yeah. Did you, by the way, have you seen the Skype conversation between Oakley and Sleeping Warrior?
between Oakley and no, I don't think I have.
Okay. Yeah. There was I don't want to get into it. I don't want to make this like a bash session or something.
Sure,
But
sure.
yeah, if you just looked it up, look up Lighthouse Skype Nathan Oakley, something like that. That'll do it, I'm sure. Lighthouse Skype Nathan Oakley. That ought to do it. You'll get that they accidentally included a Glober in their private Skype one day during a live debate, and he recorded it. And so we got to see some reveals that were pretty damning. Yeah, about what they actually about being forthright. If giving them the absolute benefit of all doubt. What we saw was them very much behaving like lawyers, which is, do not reveal this evidence. This will kill us. Don't reveal.
Yeah.
Yeah. So, yeah. Anyway,
I think I've heard mentioned that either Oakley or Quantum Erasure had said somewhere, maybe it was this, I don't know, said somewhere, don't bring this point up because we don't have an argument against it. But which goes very well in line with.
That sounds about typical. Yeah. The other thing to Google search was perfect globe proof. The phrase "perfect globe proof" appears from Nathan Oakley. Nathan Oakley typed the phrase "perfect globe proof," and it would have appeared to me, again in his defense, that Sleeping Warrior didn't know what was going on. Really, he was just going, okay, Nathan says don't say it, I won't say it. Anyway, I did want to get back to the units.
Yeah.
The units of a gram of force. Nobody's scales read out in newtons. They all read in grams of force. Even the ones in physics classrooms mostly read in grams, from what I've seen.
So
you have Newton scales at your school?
So I haven't actually. I'm actually new here. So, and because of COVID, because of the pandemic, I haven't actually gotten to use any of the physics equipment here. But what's fairly standard is a triple beam balance, and so that's going to give you. Obviously, that's going to give you a measurement in grams. However, again, you kind of have
mass
going on there, and that's going to give you mass.
That would give you mass. What I'm talking about more is just a spring scale. Like if you like a fish scale, and you hang something from it. Okay, how much does that weigh?
Those are I've seen those. Those will give you will give you force in newtons or weight.
Yeah, you've seen them in newtons. Okay. Some of them just show force in grams, and everybody seems okay with that. And my thinking is that those of us who are comfortable with math should have no trouble converting from grams of force into newtons.
Okay.
That's not even hard, right? I mean, okay, fine, got it.
Well, it's the problem I have with that, and I really don't want to try to be semantic about this, but in order to make that conversion, you have to assume what G is, which isn't always the case. And as an astronomer, it's very rarely the case.
Well, no, actually, you don't have to assume anything about gravity. You just accept that that's the unit conversion.
1 gram of force. So you're saying that if I were to weigh something, if I were on the moon and I were to weigh this pen on a scale and it gave me 1 gram of force, then how do I get a mass?
No, you don't. That's not an appropriate thing to do.
Okay.
I would say, to be proper, you could say that I'm approximating the density of air as very, very small. I'll approximate that as 0 and get an approximate mass from that. But if you put it on a spring scale, Put it on a spring scale, like your kitchen scale is, and weigh the force in grams, which is what the kitchen scale does. That you now have a unit of grams of force, and now to convert that into newtons, you would say that that is a thousandth of 9.8, right?
Where's the 9.8 coming from?
That's the unit conversion from grams of force to newtons.
Everywhere?
Yes.
Even on the moon?
That is universal. That's true on the moon. That's true in space.
It is not.
That's true.
It is not.
What's that?
It is not.
It is. It is.
I hate to tell you this.
Excellent. We have an argument. Lovely. The crowd will love us. They want a dumpster fire, right? This is two very friendly science people having a disagreement. Let me explain.
Okay.
Let me explain. A gram of force is the amount of force expected from a 1 gram mass on the Earth.
Okay.
That is what a gram of force is, because it's a spring scale, right? So if I weighed a 1 gram mass on the moon, I would not get 1 gram of force. I would get 1/6 of a gram of force.
See, this is where your definition begins to become, I think, problematic, because you have to go further than that. You have to say, well, with 9.8, at least with that kind of precision. Well, if you want to get more precise, say 9.81, if you want to do more in-depth measurements or experimentation, then you're going to have to say that is the conversion on Earth at sea level.
Mm-hmm.
So it starts,
but that's
a little bit more cumbersome to do that, because it seems to me that conversion is very location specific.
Okay, let me try to challenge you for a moment.
All right, sure.
Why are you insisting on converting this to mass? Where is that even coming from?
That's coming from, if I wanted to talk about if I put this on a rope, and I want to know what the period of oscillation is given the length of the rope, how would I determine that?
Well, you would have to determine the mass of the object.
But
we're not talking about the mass of the object. The mass does not appear in this equation.
No, but you asked me why I would want to do that conversion.
No, I mean, why do you insist on it? Right? I just want to use grams as a force unit because my scale reads in grams.
Sure.
And the point where you're hitting the wall is no, grams is a unit of mass. And I'm saying that actually I have heard my own physics professors use these terms. In fact, what we usually use is we do it for pounds because no one wants to use slugs. So we use pounds mass. Have you heard of pounds mass?
I think so, but when dealing with teaching or when dealing with scientific research, I never use imperial units. I certainly do not use British imperial units. So, because again, you're right, and I think one of the reasons that's so problematic with the imperial unit system, other than it's slightly arbitrary, is that you have this sort of inherent contradiction within what is a mass and what is a force. But I am not insisting on using mass. You asked me why I would want to convert grams of force into grams of mass, and in that sense, the reason why I would want that is if I wanted to do an experiment instead of submerging this pen into a glass on a spring scale, figuring out what the period of oscillation of this pen would be if I attach it to a string of known length. Now,
that's fair, but I want to emphasize that when we're talking relative density, we're not taking periods of oscillation, right? We're talking about why do things go up, why do things go down, and as far as I've seen, no flat earther has ever gone to how hard does it go up or down. I've introduced this into this equation and tried to get them to accept that.
Well, Sleeping Warrior and I think Raichi has also actually will tell you that their explanation is, as far as I can remember, and this is where it gets a little bit, again, squirrely as to whether or not the subtraction or there's a division. But essentially, the larger they will, I believe, and they can correct me if I'm wrong, I believe what they'll say is that the larger the disparity between the two densities, the faster that object will go. So if you put say, for example, if you put let's say a tin ball in water and dropped it, it would fall through the water at a certain rate. If you dropped a lead ball in water, it would fall faster.
Yeah, I think Sleeping Warrior insists it's a ratio, but Raichi agrees that it's a subtraction.
But even if you do the subtraction, you're still going to get a larger amplitude, which in turn to them means a larger force.
But it does. I agree with them. I would say that if you do the subtraction, I would say that Raichi was correct, that the amount of force you get is larger if your difference is larger. Not ratio, but difference.
Yes, yes. I think Sleeping Warrior will also say, basically, I've never really, I could be wrong about this, but he has said words to the effect of the disparity between the two. If you have a larger disparity between the two, the faster the object will go. And actually, that's not true because all things.
Okay, go ahead. Explain.
Well, all right, if you want to get into the minutia of it, then yes.
Well, I don't, but but sometimes we need to.
Anyone take a lead ball that is of 1 centimeter in diameter. Take a wooden ball of 1 centimeter in diameter, and you drop the two.
Mm-hmm.
According to them, the lead ball will hit the ground first. It will not.
Did they say that though? Yeah. I think
Sleeping Warrior. I have a screenshot of it. Sleeping Warrior says it does. A more dense object will fall faster through the same medium.
Well,
and actually, I will even back off that statement. They will hit the ground at the exact same time.
They won't though.
Yes, they will. Even with
if you drop a lead ball and you drop a wooden ball from, let's say, 2 meters, right? You're gonna hold it up here. 2 meters, you drop them. You're going to find air resistance is a significant difference between those two.
They are a sphere of the same radius. No, you won't.
Oh no! I've got you, sir. I've got you. Yeah, the force scales with the volume of the object.
Yeah, but the same radius, then therefore they have the same volume.
The force of downitude. Right, the force of dropity scales with the volume of the object. I think we can agree.
I'm sorry, repeat that last statement.
The force of gravity. The force of gravity scales with the volume of the object.
My knee-jerk reaction is to say no.
Well, it certainly scales with the mass of the object.
It's going to scale with the force of gravity. The gravitational attraction between two objects is only reliant on two objects. Or two properties, the mass of the object and the distance between them.
Correct. So if I double the mass, I double the force.
Yes, correct.
Okay, so if I double the volume, I double the mass.
Not necessarily.
Really? Give me a counterpoint.
So if you're talking about the same material,
yes, a constant density
because that material has the same density. But what I'm talking about is you take two balls that are of different, distinctly different densities, but they have the same volume, or they have the same radius, so therefore they have the same volume. Those two objects are going to fall at the exact same rate. They're going to accelerate 9.8 meters per second squared if you're standing on the Earth at the surface.
Yes, they will accelerate initially at the same rate. And the reason for that is F equals ma, right? Force equals mass times acceleration. Acceleration equals force divided by mass.
Yeah.
Okay. Assuming a constant density for the object.
For both of them, yeah.
Yeah, then mass is density times volume.
Yes.
Right? I can write that on here. I don't need to. So the way I work it out, the force according to my equation over there, which includes both gravity and buoyancy in this equation, the force scales directly with volume. Mm-hmm. And the F equals ma, the mass then will divide out, and you'll get a constant acceleration regardless of density.
How is the mass going to divide out?
Okay. Yeah. Let me do it. Let me just like give me an equation here. Let me insert an equation. I don't know. You know what? I'm just going to type it. I'm not going to use fancy letters or anything.
Sure.
So we got. Let's distribute the densities, right? So F equals K PO VO, right? Minus K PM VO.
Yeah.
Okay. And so that's an O. That's the force. That's the force of downity, right? Force of dropity, if you will.
Sure.
And we have F equals ma, right? So F equals ma. So let's solve for A.
All right.
Let's say here, give me A equals F over M. Okay, and guess what? POVO is MO.
Okay.
So so let's put that over here. Let's say right there. Put that right there. That PO, it's not PO, it's rho O, is MO.
Sure.
MO right there.
Mm-hmm.
Okay, and the force of buoyancy is, you know what? It's going to work out better if I keep it with the densities. Let's do it on this one.
Okay.
Let's factor out the density on this one. Mm-hmm. So that is PO VO is the acceleration, right?
Yes, that's correct.
Okay, so the acceleration is, that's my force, divided by rho O VO.
Yep.
Okay. What I'm actually going to get, and I did not expect this, but what we're actually going to get is, that's a K, by the way. Nobody caught me.
That's right.
Yeah, and somebody is asking, where's G? G is K.
Yeah, essentially.
Yeah, I'm just trying to, again, I'm trying not to scare off our friends who don't believe in G, right? So if we go straight from G, they will immediately shut off the video and then we're done. So I'm going to say, okay, hold on. Let's not call it G. We're going to call it K, and we'll investigate how it works, and then we'll investigate where it comes from. That's what I'm trying to do. So far, no such luck. Okay, so the POVOs are going to cancel out right there.
Sure. Mm-hmm.
And here, this is, oh, there you go. No, that's fine. And that is PO. There you go. So there it is. There's your acceleration, and volume has been canceled.
Yeah.
So acceleration has nothing to do with volume. But let's do aerodynamic drag now.
Okay.
Aerodynamic drag does not scale with the volume of the object. It scales with the area of the object.
Correct, which is a function of radius.
Which is a function of radius squared.
Radius squared. If they are of the same radius.
Volume is a function of radius cubed.
Yes, but if the two objects have the same radius, the drag on each object is identical.
Okay. The drag on the objects is the same. Yes, but the force is not. Because the force still has divided by the density of the object.
So
the force that you got, the acceleration is not, right? That's what you've missed, is that in one case you were working with forces, another case you're working with accelerations. You got to divide by the mass.
one second.
Okay.
So I'm just looking at that.
Okay, I'm going to do aerodynamic drag while you're thinking.
Okay. No. I mean, aerodynamic drag can be eliminated because essentially the amount of drag, unless you're going to say that the drag is density related, then the amount of drag on both objects is going to be zero, or is going. Excuse me. The drag on both objects is going to be identical.
Let's call it Q S. Yeah, CD times Q times S, where Q is the dynamic pressure, has the velocity squared in it. Not important to us because that we're going to say that's the same, right? But S is the area, the surface area, or the reference area of the object. Okay, so that's the drag. Yeah. So the net force, let's do, I don't know, net force on the object is, so total force, what are we going to call total force? So Fn equals Fo minus D, capital D. Agreed? Force of gravity minus the drag. Okay.
So
on some math here.
We'll say that Fn is the dropity force minus drag.
Right, the dropity force, right? The force of dropity. Actually, do you know AB science?
I do.
I'm totally stealing his word though, but he calls this term, or
the Riley.
He coined a term that I want to call this the dropativity of free space.
Oh, that I hadn't heard. I would have thought that he would have called that the Riley coefficient.
I would have, if Riley would have embraced this, I totally would have gone ahead and called it that.
Because AB Science basically did something that I think you were kind of trying to do, although his rationale was different. He actually tried to develop a mathematical representation of RDD based on what Sleeping Warrior had to say, and he had to come up with the unit of conversion, which he then called the Riley coefficient. But anyway.
Yeah. Yeah, he did it, but he insisted, Sleeping Warrior insists on a ratio. And I was trying to point out to Sleeping Warrior that it is not a ratio, and we can show that it is not a ratio, that generates the amount of force. The amount of force is based on this subtraction, I say. So here's what I got. I'm going to do this, right? I'll factor out the VO again, just because it's... All right, we'll do that. We'll factor out that VO. Okay, now let's plug in what the volume, let's say they're spheres, right? So what is the volume of a sphere? Who knows the volume of a sphere? Anybody?
It's 4/3 pi r cubed.
I agree. 4/3 pi. I'm just going to say pi. Oh, that is not what I meant. Could have done it as an equation. Let me just do it as text.
Okay.
I don't know. It's letting me do it now. R cubed. Right? And now the S, what is the surface area of a sphere?
Oh, surface area of a sphere is pi r squared. Well, it wouldn't be the surface area of the sphere. It would be the surface area of that which is encountering the drag.
We could define the drag coefficient either through surface area or through cross-sectional area. Cross-sectional area is easier. Yeah. So let's do pi r squared.
Yeah.
Okay, so now we see that the force acting on our object scales with the density of the object times the cube of the radius, and a constant that has nothing to do with the density times the square of the radius. And so if we take two balls of the same radius Let's say the radius is, I don't know, like, what is the radius going to be? 2?
1. Let's just do.
Is it 1? Okay, let's just make 1. Make radius 1 so that we don't have to multiply that. Then these term is the same on both.
Okay.
This term, though, has the density times 4/3 pi r cubed, right? And so you're right that it's a misnomer that I'm focusing on this r cubed. That doesn't have anything to do with it, really. The fact is, though, that there's a density multiplied on that one. So the one object will have a larger term here than the other object does. The steel versus, what we say, lead and wood. So lead has, what's the density of lead? 12, 10, something?
No idea. I could Google it.
Let's say it's 10. And let's say wood is about 1. Depending on what kind of wood it is. So they both have the same drag term, but the weight term is substantially larger for the lead. And you can see that again if you just put it on a scale. The lead on the scale, the wood on the scale, the lead weighs more.
Yes. Okay.
So they have the same amount of aerodynamic drag.
So
they don't have the same weight.
So your contention is that if you drop a lead sphere that is 1 centimeter in diameter and a wooden sphere that is 1 centimeter in diameter, then the lead sphere will hit the ground prior to the wooden sphere.
Yes.
We don't see that.
Yes, we do.
No, we don't actually. You can.
Yes, we absolutely do.
Okay.
Okay, let's do it. You ready to do it? You up for it? Let's do it. Here we go. No, is this
actually before you do this, I want to ask you. Google hammer and feather on the moon.
Well, now, what's the aerodynamic drag on the moon, sir?
0. But as you've said,
then you dropped that term.
No.
You dropped my second term.
Because you yourself said that the drag term is meaningless.
No. I said that they have the same amount of force.
You said
the same amount of force will not generate the same acceleration on 2 different masses.
The drag term on, you said that the drag term on this equation is irrelevant because it has nothing.
No, I didn't. I don't believe I said that. Did I? The CD would cancel out. If I did, now we are talking about a vacuum. Somebody said we're not talking about a vacuum. Let's get the acceleration. The acceleration is all of this divided by the mass.
Yes.
Okay. So let's divide out the mass. That's not right. Let's I make it not mess with me.
Before we do this,
I
just want to ask you a very clear question. The CDQP or the CDQ pi r
squared. That's what that's supposed to say.
That is the drag term.
Yes, right? This is the drag term.
How is that drag term related to the density or mass of an object?
Not.
Therefore, if it's not, if the 2 objects have the same radius, then does that not follow that the drag term on both objects would be identical?
Technically, we get into like materials are different, but let's say it is. They're painted or something so that they have the same surface. Then, they would have the same amount of force.
The drag component would be identical for both of them, correct?
The drag force would be identical.
That term, the C, D, Q, whatever, that term.
Yes.
If they're identical, then they can go to 0.
Yes.
Therefore, vacuum isn't an issue.
No, that's not fair. Just to say that they could go to 0 doesn't mean that they do go to 0.
But they do go to 0.
On the moon?
No.
But not here, they don't.
They don't, but they're irrelevant here because as you've stated, the drag force is identical for both objects.
Okay, all right. Let me try and write it again, just simple, because this is a mess, right?
If I'm wrong, is that not what you're saying?
Let
You,
me warn you, I'm an aeronautical engineer.
okay.
So that is drilled into my head pretty hard by the, okay, if you think, any viewers who think that means I just am repeating what I've been taught. No, that just means I have a lot of experience with this particular equation. And what we're saying is that the net force is the dropity, the gravity force, the weight. Can we call it weight? Weight-ish.
Okay.
Which, yeah, minus the drag force. Is that fair?
The total is the dropity minus the drag. Yes.
Dropity minus the drag. Okay. So the acceleration is this quantity divided by the mass.
Mm-hmm.
Okay. Now our two balls, our lead ball and our wooden ball,
Mm-hmm.
they have. Give me masses for those. What would you like to use?
We'll say that one ball is. Let's do it this way instead of using materials. Let's say that one ball is 10 times more massive than the other, and they have the same radii.
Okay, so the acceleration on the one should be given by approximately that.
Well,
and I should put G on there. Let's put a G. 10G.
1 second, because again, you were talking about being an engineer. Weight has a very definite definition, so I want to be clear on this. See, that's where we start getting into, I think, an issue with this law of relative densities, because when I think of when I say that something has 10 grams of mass, that something has a mass that is 10 times the mass of another, I am not using your formulation of apparent weight.
Well, I'm disregarding the buoyancy term for now, for simplicity. Is that okay?
All right.
And so then that would just be the weight. This is your term for weight.
Yep. Okay.
Isn't it?
So mg minus drag. Yeah.
Okay, and so now I'm doing the accelerations of those objects. Should be at.
Okay. And if you take the
so here on Earth,
but the drag term d same for both.
Yes, it is. But on one, the acceleration has d divided by 10, and the other has d divided by 1, because we divided by the mass. And that dropped out of the weight term, right? The weight term drops out the mass, but the drag term does not.
Okay, so
yeah, heaviness. Eric says maybe heaviness.
The issue that I have is that I actually...
Can we do it live? Yeah, you can totally do it live. I was going to show a video
okay,
that puts it to rest.
Oh, all right.
But while you describe your issue, while I go look for that thing.
Because I've actually seen this experiment done. And
okay. Yeah, so have I. Let's see here.
Let me look. Let me see your
weights. I don't know. Let's see what we got. No, not that. Measure rate of fall. There we go.
Hold on 1 second. Go back.
Oh, go back. Whoop.
Can you click on the Viserium? The one
Good
right,
testing?
that one. I want to read that statement.
If you drop if you drop a heavy object and a light object simultaneously, which one will reach the ground first? And he's going to show us that it's approximately the same.
Approximately or exactly the same?
He may say it's exactly the same, but that's not true. It's only going to be approximately the same, and all you have to do to prove that is drop a feather.
But a feather,
yeah, somebody on the thing said, "Hey, just do it and hash it out." What do we got?
Okay.
I got a piece of paper. I got a ball.
The problem is, before you do that, because yes, the problem is before you do that, surface areas of those objects are not identical.
The surface areas are no, they're not identical.
They're not identical.
But we just did the math.
I agree. You got me on the math. For some reason, I cannot, for whatever reason, reconcile that for the moment, and that is a fault on my part. However, it's interesting that with the Viserium, with that Viserium video, again,
this is a great video. Everybody should go watch it. By the way, they literally just go and do this.
The ball. Go back. Sorry.
Yeah, which one you want to see?
I'm frustrated with myself for not being able to see the. The problem here is that those two objects are not of the same radius.
Right. They do. This is a fantastic video. Let me plug it. Let me even put it in on a banner. Yeah, I should worry about like someone's going to give me a copyright strike, but I trust these folks won't, especially if I show their link. They do a great set. They do objects of different sizes, objects of different densities, objects different shapes, and they show. And he actually goes through the calculations in here somewhere to show why. That it's you get some really interesting results. Yeah, this is what I was talking about here was drag force increases with the square of the object's length, and gravity increases with the cube. So that's as you scale objects, you see that their speed changes. So that's what that's about. What do we got here? Time in flight and velocity and how they accelerate differently, and that's Reynolds number. We don't need that. If you happen to have two objects of very different densities but the same radius, we could show that this is the case.
That's the problem with doing this with the stuff in my office, because I don't have a ball of. I do not have two objects that are of identical dimension yet of different densities. If I did, I would freely and happily perform that experiment.
Yeah, I'm looking around. I don't have anything. I wasn't prepared for this, but
to quote Ken Hovind, I was not prepared for this. But
I'm not prepared for that.
I'm not prepared for that. I have seen so the experimentation that I saw was the person took a electromagnet, stuck two spheres to it that were of identical radii and of differing densities, but obviously both were of magnetic material. I think one of them was steel, one of them was iron, and held it above a turntable, wooden turntable covered in tinfoil, and that turntable rotated at a certain speed. They then turned the electromagnet off and dropped both objects. If the two objects fell at different rates, then one would expect an angle between the two indentations. I can't show this to you because this was done to me live. It was not recorded, but that angle did not exist.
Yeah, I could prepare something. It would take some time to prepare something. I might suggest we just get like something very light and two of them and tape a bunch of pennies to one of them or something, right? So it's just heavier. But yes, the fact of the matter is that drag, when we go from force to acceleration, we divide by mass, right?
Yes.
Which is why, and the fact that we divide it by mass, that's why all things accelerate at the same rate. Yes, all things accelerate at the same rate. This is true. And it's because when you take your weight, which is your volume times your density, and you divide by your mass, or times gravity, right? It's gravity times your mass. Let's just say gravity times mass is your weight. Divided by your mass, that's just gravity. All things accelerate at the rate of gravity.
Okay.
And if you include drag, then you take the drag force, which does not scale with mass, and divide it by your mass.
Mm-hmm.
And so a lighter object is more influenced by the air than a denser object is.
Okay. All right.
And so if you drop it over a very short distance, you will not see the difference because drag scales with the square velocity.
Okay.
So if you're moving slowly, no one's going to notice. But if you drop it off like a multi-story building, like those guys were doing, you'll see that.
Yeah, you do the whole Galileo Leaning Tower of Pisa thing.
Yeah, and if you do the inclined plane to keep the drag to a minimum, also that's another way.
Well, and actually, I was thank you for pointing that out. The issue with the inclined plane, and I've thought about doing a video on the inclined plane issue, or doing an inclined plane experiment. You run into two problems in that. In one, frictional force is dependent on mass, and so how do you resolve? I mean, essentially, the point that I'm trying to illustrate is that regardless of that, two objects are going to move through space under the influence of gravity, strictly dependent on their masses and not their densities. And so friction is dependent on mass. Or yes, friction is dependent on normal force, which is in turn dependent on mass. And so how do you take that into account? The other thing, and although this can be solved again using two objects that are the same shape, you also have the problem of rotational energy in there. But
yeah, they'd have to be the same dimensions.
Yes, you would have
something though. You said something in there that I'm going to be flat earther on you here for a second. You mentioned that the weights or the normal force. You actually said normal force dependent on the mass, not on the density. But that's not correct because of the buoyant force. The buoyant force will oppose the gravity force.
Okay. Yeah.
That is what they're talking about when they say relative density. Let me flip it now, right? I've been trying to take the physics and phrase it in their words, right? I've been trying to accomplish that and getting very little accomplished. Let's be honest. Someone said it earlier. It's impossible. I think it is probably impossible. Let me now flip it. Let me take what relative density is, or at least I take what they say, shave off the stuff that's not true, and whatever's left, translate that into physics speak. Relative density is buoyancy. Relative density, the equation that I show especially, is literally like, let me just show it again here on the stream. Share. Wait, oh, I just have to click this thing. I'm pretty weak sauce at this this StreamYard stuff. This equation here, you will recognize if you just change the K to a G, that is the first, the rho naught is the weight, and rho m is buoyancy.
Yeah. And when I commented on I think during our first exchange, I mentioned that, yeah, there's a sign issue in there somewhere, but yeah, your equation matches what we would expect, given a sign issue.
Right. And for the flat folks that are watching right now, we're saying, yeah, it's all relative density. Where I'm coming from is you guys want to do experiments. You don't want to do math. You don't want to just echo something that's in the textbook. Okay, fine, let's do that experiment. And so I did the experiment. But maybe I'm cheating a little bit. I looked in the book, right? When I did the experiment, I looked in the book, and the book said, well, it didn't have this form of the equation, but I took the book's equation and I did some experiments, and I said, hey, yeah, I can prove that this formula works. I don't know why, but I can prove that it works pretty easily, and you can do that with me. Yeah, I looked in the book to get the equation. That doesn't make it wrong, right? I looked to see what the answer was, and then I did the experiment to make sure that it's correct, and there it is. So density matters. It absolutely does matter. For the density of the object will increase the weight on the scale if you hold the object's volume steady, right? So two objects of the same volume, the denser thing will weigh more. Yes, it will not initially drop any faster. If you drop them over a short distance, they're going to accelerate together at the same rate.
Well, they won't actually. By your
well,
I mean,
right. If it's buoyant, if it's actually buoyant, it'll go the other way.
Well, I mean, if it's in the sense that by those equations that you said, even at time
you're right.
0 plus.
You're correct. Let me correct that. I just neglected row M right there when I said that, which is what I'm telling you not to do. So I stepped right in it. Yeah.
Well, see, all right. So where was I going with this? I knew I should have written this down because there was a question I wanted to. So yes, you're right, and this is something that I have taken for granted, and I've taken for granted. You're correct that the thing on the scale, or the measurement on the scale, that is the apparent weight, that does involve a buoyancy force, and that buoyancy force is acting on all objects on the Earth. The issue comes in, and this is something that's rather that's sort of maybe nuanced, I don't know, is that folks like Sleeping Warrior, and I believe Raichi as well, they will claim that gravity, the force of gravity, does not exist at all. Right. The problem with that is, in order to have a buoyancy force to begin with, you have to have a downward force to create the pressure gradient in the environment. If there is no pressure gradient, therefore there is no buoyancy force, which is why you don't have issue with that on the moon. There is no significant density gradient in the Martian or in the lunar atmosphere.
Okay, now so what the RDD people are going to immediately say is there's no atmosphere on the moon. They're going to say there's no moon, right? But
yeah,
let's do it in a vacuum chamber, right? We'll do it in a vacuum chamber, and then they're going to say the density is 0. So of course everything is heavier than 0 when it goes down. Even helium goes down in a vacuum because the medium is 0. Right, and so that's what they're going to say, and they're going to very much complain about your requirement for gravity.
Oh, of course,
buoyancy, very much.
So how would you combat that?
Well, the way I've tried to combat it is by not calling it gravity, but insisting that we measure it. I am trying to get them to agree. And so far, the only one that agrees is Bob from Globebusters. Bob actually agrees
Bob is
that,
I need to look.
we measure a downward force.
Mhm.
We do. And I think Rachel's on the verge. When I talk to Rachel, she pauses and she's unsure because deep down, and Rachel, if you're watching this, deep down, you know there's a downward force. We have not proven that it's gravity. She and I have not discussed that it's gravity at all, but we do know that things drop, and she's agreed that if there's no density gradient, that things will drop.
When you say density gradient, what do you mean by density gradient?
Yeah, that's a word that I think I've kind of introduced to them. I think they've embraced it. Is that the density is not the same everywhere?
Okay.
Within a medium, within the medium, within the air, that it's dense air here and less dense here. They all agree that that's the case. Well, most of them agree that that's the.
I was going to say
that most right, right. Okay, if you don't agree with that,
then again, you don't know where you're going to go with that.
Yeah, that's super easy to show. It's denser here than it is here. And so then the question becomes, the first question is it denser here because it's denser here? Or is it denser here because something made it that way? Right, and that even sounds ridiculous and circular as I say it, but it's not entirely ridiculous. If you think that, first of all, an object will be forced to move based on the difference between its density and the density of the material that it's in, right? And I think we can agree, yes, that's called buoyancy. The buoyant force.
I'm sorry, I missed your last statement. So, okay. I just want to be sure.
If an object is suspended in a medium that has a different density than its local medium,
yes,
it will move.
Yes.
Here on Earth, like just static here on Earth, making no assumptions about gravity. But we observe that things fall. Things that are denser than their medium fall down. Things that are lighter than the medium move up. And they have an apparent net force that is given by the difference of the medium and the surrounding, the density of the object and the surrounding medium.
Mm-hmm.
Okay, so we got that. Then the next step is what gives you direction. And so far, they are mostly sticking with that when the object starts to move, if it's moving towards a more dense area, then it has to follow the density gradient down. So the density gradient would be defined as a vector quantity from the least dense area to the most dense area. Mm-hmm. Is going to give you the direction. And so they seem to use the density gradient as their direction.
Yes.
And Sleeping Warrior will not engage with that. That's too mathy for him.
Yes.
Raichi thinks maybe that's correct sometimes, but not correct other times.
Okay.
And so what I'm trying to do right now is get Raichi or someone like Raichi, ideally Raichi, to say for sure, no, that is what it is. That is. If you have a density that is, it's more dense here and less dense here, right? And then my object is say heavier than the medium, it must go towards wherever I put the more dense object. It has to go towards the more dense area in the medium. That's what she thinks is happening. And Sleeping Warrior is very firm that is what is happening. He won't use the word gradient, I don't think.
Yeah, I'm not certain about that.
Okay. But as I was trying to talk to her about that, I realized she's almost correct. I almost completely agree that Rachel is right about that.
Okay.
Because, and you said it, what makes it move for us is the pressure gradient.
Yep.
There's a difference in pressure from one area of the medium to another area of the medium. And so if you integrate, and I'm going to talk math for a second, if you integrate the pressure over the surface of the object, you get the net force acting on the object.
Yeah.
So if there's a gradient of pressure, that will give you the direction and magnitude of motion of the buoyant force.
Yep.
The buoyant force.
The buoyant force is always going to be in the, as far as I know, I'm just going to put this out there. I'm going to say that the direction of the buoyant force is 180 degrees away from an increasing density gradient.
Yeah, right. And that was what I was trying to show with one of my videos, where I said, okay, the next experiment, what we do is we hang a helium balloon in a car and we accelerate and we hit the brakes and we see the angle, the angle that the balloon hangs at is going to match the angle your accelerometer says on your phone. This accelerometer will tell you how much is down and how much is forward back. You make an angle out of that, it's going to match the balloon. Didn't really get anywhere with it, to be honest.
I know that Smarter Every Day did a video. I'm sure. I'm sure other people have done where he showed the balloon deflection. I don't think he used accelerometers, but
right. Robert says density disequilibrium cannot predict the motions of the planets. That's correct, but of course, if you are a science skeptic, is the word I'm using. Science skeptic that does not believe in planets, that's really not going to convince them. Right.
Yeah, I fully agree with that. And that, yes, density disequilibrium will not predict the motions of planets. The problem that from an astronomer point of view, and this is somewhat of a divergence, I apologize.
No, that's okay. You're an astronomer. Let's talk astronomy too.
The astronomy point of view is that there are just a vast number of things that we see as astrophysical phenomenon that cannot be explained by density disequilibrium. The problem comes into they will just say that that's fake. They will say that those are luminaries. Well, no, let me backpedal on that. What they will say is that what you're looking at is a projection on the dome and on a firmament.
You're going to get all kinds of answers.
But essentially,
ultimately, it all boils down to we don't know what those are. Stop drawing conclusions from them. That's ultimately what you're going to get.
Yes, exactly. Just because the planets move in a certain way doesn't mean that gravity exists. It just means that the planets move in that way because they're projected to move in that way. Let's ignore the fact that we can perfectly predict their motions, but they just happen to do it. And so, for a lot of astrophysical phenomena that I can use to sort of debunk this idea of disequilibrium, it gets no traction because they can easily just separate themselves from anything projected onto a dome.
Right. Alan, if you're still in here with us, maybe you weigh in on this. It seems to me that the argument, we don't really know what those are, we should not draw conclusions from them, is actually kind of a reasonable argument. It's fair from at least a certain point of view. But I always stumble when I get to but we did measure it. And look at what we found. And holy moly, it sure looks like a sphere, right? You watch the stars, watch the star rotations, and you say, oh, that's not really a sphere. Okay, maybe it's not, but it sure as hell looks like one, right? It looks like a sphere, doesn't it? Right? If there's any of our skeptics in the crowd there tonight, I would love to hear your point of view of, doesn't it look like a sphere? Like when Rob tracks a planet going around in the night sky, and he tracks it throughout the year, and he draws what that thing is doing. Gosh, it looks like gravity's working on that thing. So, if you completely do not believe in gravity, at least maybe you could grant us an understanding that we were fooled into believing it because it sure looks like it.
Because, and if you want to take it from your perspective, from an empirical perspective, let's go all the way back to Kepler. I mean, Kepler's observation, well, Kepler took Tycho's observations primarily of Mars, and he derived 3 empirical laws based on those observations. That planets orbit around in ellipses, that basically equal areas and equal times, that planets will move faster when they're closer to the sun than when they're further away. And then finally, the period of the planet is proportional to the size of that orbit. And that has nothing to do with gravity. Kepler never invoked gravity. He
didn't invent the thing, right?
Yeah. He just described what they did. He actually, as far as I know, and I haven't actually read I can't even remember what document he wrote his laws into. Anyway, I haven't read that. So I don't know if he attributed any sort of force to it, but Newton came around and Newton said, okay, I can explain those things. And actually he re-derived Kepler's third law, his harmonic law. And he determined that actually in a more general sense, if you include the mass of the object, you can actually use that relationship to determine the mass of Jupiter. You can determine the mass of the sun based on the orbital period and the semi-major axis of the planet. And so we actually, because of the prescription of gravity, we actually have a better understanding of what's going on. So if there's a flat Earth, if there's a skeptic out there, I would be very interested in seeing if someone can apply relative density disequilibrium or any other alternative gravity theory to observations of Mars or any of the luminaries, if you want to call them that, and actually come up with a model that can predict their motions as well as we can do it today using gravity.
Right. So Alan is here. Alan says, I agree that it does look like a sphere, but if it were a sphere, how is it that we see them as 2D circles if light reflecting off a sphere would not light up the entire object? And Alan, thank you for being here. I really appreciate you and your tone on everything. The tone that I do not like is the one where this question is asked in a disingenuous way, where someone says, oh yeah, but I know it's not a sphere because blah, 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 blah. And ultimately, that is what we get with a lot of the skeptics. Skeptics very often have a very angry tone towards science, and they have a very dismissive tone where they are declaring that they are smarter than any scientist ever.
That I'm not even a scientist. That one I really appreciate.
Right. Oh, Newton, Einstein, those guys were morons. I disproved them in my pajamas last night, right? And that's not an attitude. That's not a look you want, right? You don't walk around saying that. I must be. Einstein was the smartest man ever. He was a chump because he didn't even realize that gravity wasn't real.
Reminds me of Princess Bride. I don't know if you've ever
yeah.
Moron.
Right. But Alan, we could talk about this. We could look into these questions. They're good questions that you should ask.
So to directly to ask this question, I'm a little bit confused as to the question. You state that, let's see, if it were a sphere, if the planet were a sphere, how is it that we see them as 2D circles when reflecting it light off a sphere doesn't light up the entire object? Now, the reason for that.
Hold on a sec. I want to answer Alan real quick because I may have misspoke or said it badly. I really appreciate you, Alan, because you are genuine. And I understand that Rob and I think, are both on that. No need to apologize. We really appreciate this question. And Rob's going to now answer you. He's an astronomer, so he's going to answer you. Go.
So there are two things to keep in mind. When you look at the planets, if you look at planets that are what we call superior planets that are at further orbits, Mars, Jupiter, Saturn, what have you, what we're looking at is we are looking at essentially we are looking at the entire illuminated face of that planet. And so the dark side, the side of the sphere that is not reflecting light, that is on the opposite side of the planet. And so therefore we don't see it. And so that therefore we see it as a two-dimensional or a 2D circle. If you were to look at the interior planets, Mercury and Venus, however, we don't see them as 2D circles, actually. We actually never see them as 2D circles. We see them in some kind of phase, meaning that we see them either as a crescent shape or a gibbous shape, which I eventually learned comes from the Latin for hump. It looks somewhat circular, but it isn't quite fully full in lunar terms. So, and the reason for that is because of our perspective. So for Mars, if the sun is you and I'm the Earth and this is Mars, then Mars is way out here. Put myself in way out here. We're seeing the illuminated face of Mars. But if this is Venus, and again, you are the sun and I am, obviously me, then if it's like here, I can basically only see a very thin slice of Venus. As Venus goes around, this is failing completely, but as Venus goes around, I can see more and more of the illuminated surface. And so the planet grows in phase, very much like the moon does, going from a crescent phase to a quarter phase to a full phase.
So yeah, what I just threw up here for you is, like, imagine that's the Earth. That's you. That's you. And ask yourself, what can I see from here? Let's say that's Mars. The sun, right? So Mars is lit like this, and you can only see the lit side, right? And the inner ones, yeah, and that's really great. We mentioned that earlier. I don't know if I said it, but a couple years ago, the Pasadena, where I'm at, the Pasadena amateur astronomers were out, and they have some pretty good telescopes that they just let people look through. And the first feature of the evening, before the sun was even really down, was the crescent Venus, was a crescent of Venus. And that's, yeah, we only see Venus at sunrise and sunset because it's always near the sun, no matter where you look. No matter where it is, it's got to be somewhere near the sun. So you only get to see it when it's just right at sunrise or sunset. And when you do, you see a little crescent shape or a gibbous shape, depending on it's in the front or the back. And that's what you get.
Yeah, Venus is never going to be further. It is never going to be more than 37 degrees away from the sun in either direction. That is what we call the greatest elongation of Venus. And so when it's at greatest elongation, then it is as far away from the sun as it is ever going to appear in the night sky. And so I recently saw a video where someone was claiming that they saw Venus and the full moon in the night sky, but that was quickly debunked by the people who took the photographs or took the videos, and the moon was not full, or Venus, or what he was claiming to be Venus was not actually Venus. But so the Venus is only visible in the early and morning skies. And so
my diagram, not to scale here, but you see the wedge that Venus has to stay inside that wedge. It can't get out of there, right? So it's always going to be near the sun.
The same is true with Mercury, but Mercury is an exceedingly hard planet to observe because, one, it's smaller, so it's smaller and it's further away, so it's not nearly as bright as Venus is. And because it is close, its orbit is smaller, it's actually closer to the sun. And so the timing is such that the sun is almost always going to be in the sky, or the sky is going to be really bright, so that you can't really pick out Mercury from the night sky.
Right. Did you get to see the transition a couple years ago?
Oh, you mean the transit?
The transit, yeah. The Mercury transited a couple years ago. 2 years ago?
I have only actually seen Mercury through a telescope twice in my life. Actually, yeah, through a telescope twice in my life. Both of them were during transits. And when I say that, and I want to clarify this, that both times that I did so, I was using a telescope that was properly shielded for looking at the sun.
Right.
Do not look at the sun without a filter on a telescope. Do not do that.
Yeah, I didn't
really want to be blind.
I thought I was just going to get to see it online because, of course it was live streamed and everything, but actually I was hustling to class. I was hustling off to class to my office so that I could get on the computer and watch it before it was over. But lo and behold, on campus, there were two guys were set up with their telescopes, with their solar filters, and as I just running past, I'm like, oh my God, can I look? And they're like, oh yeah, come on, look. So I got to see that. Yeah, is it dangerous? Don't look at that. Yeah, don't look at that with the naked eye. Don't look at that through a camera. Don't look at that through. I mean, the camera won't hurt your eye, but it might ruin your camera.
Yeah. The issue is I actually during the last transit, I was actually in Louisiana, and I set up a telescope which was had a cap solar filter. And what we mean by solar filter is, think of these filters are very much like welder's glass, and they block out something like 90% of all incident light. If you were to actually hold up one of these filters during the day and try to look through it, it would appear opaque. You wouldn't be able to see through it at all. The only thing you can see through a solar filter is the sun itself. That's the only thing bright enough to actually go through the solar filter. So yes, it is dangerous for a couple of different reasons. There is so much light coming through that if you were to look at the sun under any kind of magnification whatsoever, that's going to burn out the cells in your retina. The other issue is you have no nerve endings in your eye. So you're going to go blind and you won't even notice. You won't even feel it. And then lastly, and he was talking about the damage to the instrument, is that particularly if your telescope is of any good size, when you magnify light, you are also magnifying heat. And so you're going to cause significant damage to any sort. If there are glued components within that telescope, that glue is going to melt.
Ants in a magnifying glass, anybody?
Yeah, exactly.
The telescopes that you're talking about are bigger than most magnifying glasses. Good at, maybe that like that for a good one. That's a big old magnifying glass.
Oh yeah.
Right?
But you can get, and I really wish I had one in here. If you're really curious about this sort of thing, if you really want to look at the sun safely and look at, transits or even sunspots, there's something called a sun spotter. It looks like a Masonic symbol, actually. So it kind of looks like this, where essentially, and I always get the wrong, sunlight will come in through an aperture. It hits or basically a pinhole. It goes through an eyepiece and then gets reflected and down onto this. So it's called a sun spotter. I think they're around $20, 20, $30. So they're recently in
a with a mirror.
So yeah, it's an eyepiece, and the light gets focused through the eyepiece. That's your telescope, and then that light hits a flat mirror, and that light gets redirected down to basically a screen at the base, and that will create an image of the sun sufficiently large that you can actually see transits of planets or large sunspot groups, that sort of thing.
Yep, very, very cool. Okay, well, it's coming up on 2 hours, so let's probably start to wrap this thing up. I know it's super, super late for you, Rob.
3 in the morning, but I'm an astronomer. I like to work nights.
Yeah, I figured that's true. You guys are always up at night, aren't you?
Yep.
All right. Well, that's cool. What did we say? Talk some astronomy. We talked relative density quite a bit. My whole thing about relative density is, and this is something for you, and that is, I think that that science skeptics are created when they have a negative interaction with science. I think that these little microaggressions that we inflict upon people drive them sometimes to choose to say, these science guys, I don't trust them. I don't like them. I don't associate with them. I don't believe them. And then someone else comes along and is willing to say, these science guys, they're all a bunch of liars. Look what I can show you. And I think we have a hand in that as science educators, science communicators. I think maybe, I'm not sure, but I think maybe we have a hand in that, because how many skeptics have you heard start off with gravity is not a force?
Most.
Yeah, I think that's one of those pivotal moments. And I pushed back from the textbook and I looked at that and I said to myself, I think I said that. I think when I said that, I said it because I wanted to feel superior. I think I wanted to impress my peers with my scientific knowledge. I don't think I actually said that to educate anyone. I think I said that because I wanted to feel superior.
Wait, you said that science didn't exist?
No, when I said gravity is not a force.
Gravity is not a force?
Gravity is not a force. And I said centrifugal force is not a force. Centrifugal force, oh, it's fake. It's a myth. It doesn't exist. I said those things. Yeah. And I'm now advocating to science communicators not to say those things, to instead just say centrifugal force is an inertial force.
Yeah.
You say, somebody comes to you and says, hey, I heard gravity's not a force. You say, well, you know, in four-dimensional math, we can show that gravity is an inertial force, but that's a force. Can we just say that? Can we just agree to that? Yeah, that's a force. It's a kind of a force. And if we're going to do four-dimensional math, then we can show that it's actually an inertial force. And you say, what's an inertial force? That's kind of like centrifugal force in that it comes about in some kinds of them. If you look at the math in one way, it's there, but you just look at it in a different way and it goes away. And it's because of the way we're looking at it in the math. And if we had just said that to people, then maybe they wouldn't hate us so much.
Maybe.
Maybe not.
I will say I will say this, that I came into a little bit of a flack because I think the argument got started with Sleeping Warrior, and then someone else picked it up. I can't remember the gentleman's or the person's name. And we got into an argument about whether or not gravity is a force. I contend that it is. I know relativity is a thing. I understand that, but and I almost look at it as a semantic argument in the sense that gravity, the presence of mass, causes things to attract to each other, which to me, that's a force. I mean, for me, it's an easy way of describing things. But more generally, and kind of getting more to your point, is there's a quote that I like to paraphrase because I can never memorize it. It says something to the effect of, "No one's mind has ever been changed through insults." And so, yeah, I very much agree that Sleeping Warrior again is an excellent example of this. I have been following his career, as it were, for probably too long, to be honest with you. And when he first came on the scene, and Simon Dan and Conspiracy Cats were making debunking videos about him, he actually seemed like a really reasonable, kind of chill dude. But particularly after the experiment, the egg experiment, and he got nominated for Dumb F of the Year by Fight the Flat Earth, I think he in a sense got radicalized by Nathan Oakley. And now he is just a raging D-bag. Like he is. I really, even now I don't like saying that. He acts irrationally angry. But I can see where he's coming from, is because if I had to take that much flack from people, and I actually defended him at one point in the comment sections of these folks, because I was like, yes, the egg experiment is flawed. But he tried something. Unlike Oakley or Quantum Razor or Ranty, he actually tried to do an experiment. I was like, this should be applauded. We shouldn't really make fun of him. We should, at the time, taken steps to realize, done sort of an A/B science approach of, you're on the right step, but these are the issues that you have with your experimental design. But no, that's his "I'm smarter than Einstein" moment.
Yeah, I agree with that. I don't want to bash anyone. That's not what this channel is about. And the main reason for it is that I have learned that the more you trash somebody, the more you just divide into teams, and we just hate on each other. It's the Lakers and the Knicks, or it's the whoever. You pick your teams, and we just hate each other, and there's nothing more rational to it that happens at that point. And yeah, I've watched Sleeping Warrior ever since I got off on the wrong foot with him right from the beginning, as I mentioned. But I felt very much like you did, that I thought that was a good experiment, and I thought that I could reach. I thought that by embracing relative density and pointing out the correctness, because there are people, it is so divided that when somebody comes out and says, hey, density matters, guys, density matters, I can see that. And then people will shout at them, it's not density, it's not density. And like, pump the brakes, guys. It absolutely, density is in there. It has something to do with it. It does. And let's embrace it. And let's take a look at what are the density, what's the relationship? How does that work in there? And so that's where I started with my Science for Skeptics series. Was all about that. It was like, look, I don't want it out of a textbook. I want it on my own, that I can do as an experiment. And I know that density has something to do with it. let's do that. And I thought that I could ease in to, here's an equation that works. Test it, you guys. Get in the kitchens and prove I'm wrong. If you think I'm wrong, all you got to do is get up some combination of materials that this doesn't work. And I contend, I don't think you can. I don't think you can prove that that's wrong, because I've tested lots of different materials. And then I go on to, okay, and now down is a thing. Stop trying to deny that down is a thing. Down is down, up is up. Can we just agree on that?
You're you're gonna get into it with Sleeping Warrior, because he's not going to say that. He's going to say that up and down are not things anymore.
Right. He won't agree that up is up and down is down now. And
which is why I become very, very specific in my language. I try to use terms like towards the ground, away from the ground, which I don't think anyone can dispute that direction.
Well, I think that Sleeping Warrior is still taking the position that things go toward the ground because that's where the density is. That objects are pushed because of the density.
I have a screen capture where he says, in this I can quote, things fall because, quote, the ground is denser than most objects, end quote.
Yeah. So Rachie is somebody that she represents the person I'm trying to reach, which is somebody who doesn't trust science, doesn't trust the textbooks or the science communicators at all, has antitrust for those groups,
yeah.
But is still capable of obvious, rational, logical breakdown of thought. At least I believe that she is, and if not, even if not, she's nice. She doesn't rage on people for the most part, right? And so I really appreciate that about her. And so I'm hoping that she and I, or she and all of us, can get together on some things and say, yeah, no, heavy things go down, right? They go down towards the ground, and it doesn't have, even if you mix up the density, like, and that's the beauty of it, is it would be very easy to do an experiment to prove that. But first, I just want acknowledgement that is the hypothesis that we're testing, that I have a testable hypothesis. And so far, it's been some weeks now, and so far I've not gotten anyone to firmly agree that, no, that is my hypothesis, that the object must go to where the medium is densest. And then I'll just turn the bottle upside down, right? And go,
well, if they're being honest.
Dense, not dense. Whack. Oh, look, it's coming down.
Well, if to be honest, if they really looked at what they were saying, it actually depends on how dense the object is in the medium, because in the sense that is true, I would say that is true if the object is denser than the medium. If it would fall, if it rises, then the opposite is true. It actually goes towards less dense.
Well, they have that right. They have that part absolutely right. They do. That's the case. But the assertion that it's caused by the density of the medium itself, we say that is not the case. We say there is an external force acting on the system, that the different mediums respond, the density of the medium respond differently to that force, right? That's what we're saying. So it is actually that external force is giving the direction through the pressure gradient. That's what we'll say. And so my experiment is, I don't have a bottle. You take a bottle, fill it halfway with water, halfway with oil.
Yeah.
You've got a density tower, you've got a density gradient. The densest water is at the bottom, the lightest oil is at the top. And so all you got to do is flip it rapidly so that the densest water is now at the top, the lightest oil is now at the bottom. And if the density were the driving force, it would self-sustain. It would stay that way.
Okay.
But I hypothesize that there is an external force acting on it that will drive the densest water back to the bottom and the lightest oil back to the top.
Well, wouldn't that be for them? Wouldn't they just come back and say that's what they're saying is that an object is going to move, a denser object is going to fall through the external medium of air, I guess.
Well, but if it's in a bottle, it's isolated from the air. So the air cannot influence that.
Yes, although again, I don't. This is one of the reasons why I've never commented on your video, your discussions with Rachie, is that I don't want to go off on a tangent on a false narrative, essentially. But they're going to. I mean, if you look at, they might state that, you know, if you look at the atmospheric pressure on the bottom and the atmospheric pressure at, say, the top of a mountain, obviously they're different. The densities are different, so it does affect, even though you have it in a bottle, it does affect it. But again, that's not my position. I'm putting words in their mouth, creating straw men.
Right. Dumb Jezza asks, would they say that the density outside the bottle has some influence? Rachie has firmly agreed no, that it cannot. The example I gave was basketball in a submarine. Can you play basketball in a submarine, basically, right? You're under the water. Is the basketball going to be like floating because you're surrounded by water? No, it will not. It's in an air pocket, and so the air pocket, it has to be in contact. So the medium and the object have to be in contact. We agree on that.
Oh, all right. Excellent.
So yeah, I think that if I can get them to just firmly say, yes, I think that the density forces the objects to move, then I should simply be able to turn the bottle upside down and show that that's not the case. But I don't really have strong hopes that anyone would agree with that simple, because we all know what happens if you turn a bottle upside down. We all know it. And it's incongruous with the concept of relative density. And so we all know it, including them. And so they do know. I think they absolutely understand that that doesn't work. Right. And so my hope is that I could get someone to take a middle road. Bob from Globebusters does take that middle road, that there is some external source of direction. There's an external force. He just doesn't agree that it's mass attracts mass.
Yeah. I believe his is electrostatic.
But that's an oversimplification of his theory. I thought that at first too, because he said that, and I saw that on Dave, the Professor Dave.
Yeah, maybe.
And he believes in electric universe. I think Bob has a spin of electric universe, his own version of electric universe, I think is what he's doing.
Okay.
If you're familiar with electric universe,
somewhat.
Electric universe people don't believe the Earth is flat, but I think Bob has, kind of pulled the two together.
So there are a smaller subset of flat earthers that I've encountered, more than just Bob, but that believe that What's It actually is another one, who believe in the electric universe. And actually one of the larger kind of meltdowns on Oakley's channel was What's It trying to explain that there is a downward force and it's because of electrostatics, and Oakley just kept shouting over him, gravity, go down, go boom, boom, blah, blah, blah. Or gases go down, whatever. So yeah, there is, I like the fact you brought up Bob, because he is someone I really kind of want to look into, because he is He's on record in saying that, astronomy is a science, physics is a science. And so he seems to be far more reasonable. And so I am very curious to know what his actual rationale is. And so if it's electric universe, I would. I don't know what his version is, but I would very much like to know.
Yeah, he's left me a few comments, so I know that he has found me. So I'm hoping to get some interactions going, because he has been so far very respectful, and that's really all I'm looking for. You can have any point of view if you're respectful, and I welcome that.
Yeah, he seems like a reasonable guy, and particularly the amount of crap that he's gotten because of the Netflix thing. I'm actually rather impressed by that.
Yeah.
Jaren, on the other hand, seems to be more of the antagonistic sort, but yeah, Bob seems like a reasonable. I would very much like to have a conversation with Bob about.
Yeah, I think I could hang out with Bob. I think that'd be all right. He definitely, he didn't earn honesty points from that Netflix thing, that's for sure. But I understand. I understand when your hypothesis completely blows. It just, you do your experiment and it blows your hypothesis. What do you do? Even regular scientists don't always publish, right? Publications don't want to publish failed experiments unless they're truly earth-shattering, right? Like if it's Michelson-Morley, yeah, they're going to publish that.
Exactly.
But,
if no result has physical meaning, then yes.
Right. Apparently Electric Universe is an album from Earth, Wind, and Fire.
I was going to say, I would not be surprised by that.
That's awesome. That's awesome. Yeah. Okay. So yeah, that is my hope. My hope is that we as science communicators can continue. I mean, I think most of the professionals like yourself are. I mean, we're educators, and so we don't do that. We don't do that to students. We don't tell students that they're dumb. You don't. That's not.
You're not going to get anywhere with that. They're going to shut up. Just build a wall. If you antagonize them, they're just going to build a wall, and they're not going to learn anything.
Right. And I like to tell us that we remind educators that we do things that you could call maybe a microaggression. Things like saying gravity is not a force is an unnecessary way of wording it. It's a purely semantic issue. It depends completely on what you consider a force to be and not to be. And that we don't need to go there. We need to get to understanding. And we can get to understanding. Any of these people, they're smart enough. Many of them, at least, have shown that they are smart. And we hear that all the time, that they're stupid, right?
That's
no,
too.
They are not. And there are believe it or not, there are actual studies on this that compare IQs to various types of science denial. And you'll find that the smartest people are the best at denying science.
I'd not be surprised by that.
It's incredible. And so, yeah, don't think that they're stupid. They're not. They are just antagonistic. They're just against you. They have chosen a side that is not your side, and they just want to win. And so I'm trying my best to remember to break that barrier down.
Yeah, and I applaud that, and I would love to have a future conversation where we talk specifically more on that. In that, I'm very curious on how to go about doing that. How do we, find what the rationale behind why they have the belief systems that they do, what it is about the sort of current environment that has, essentially why do they not think that gravity is a thing? Why do they not think space is a thing? What is their essentially basic assumption that gets them to that conclusion? So if we can find that out, and and so develop strategies on how to better communicate with them. But yeah, like I said, and you know, with your, I'll look into your videos and see what you're doing now that I have a better, more complete understanding of how you're approaching things. Because I know I've said it before, but I really like what you're doing, and I really would like to do something very similar. In that, if when I do actually make videos, and I will be making videos eventually, I don't want to make debunking videos because that's just not. I don't know if that's actually useful, but
some of the debunkers claim some wins. So okay, maybe it works.
Cat's got seek truth, speak truth.
Yeah, Katz is a special kind of debunker, though. I'll call him out because he's humorous, he's friendly, and he's not mean.
Yes, yeah, I agree. He's probably my favorite debunker, as it were. Although AB Science is pretty high up.
AB Science is fantastic, but he's definitely for a different kind of audience. He's for us, right? And he knows it. He embraces that. I'm mostly going off of the literature that says that what you wear matters, what you look like matters, the way you talk matters.
Really, what literature are you reading? Because
maybe I'll send you some stuff, but you may just go Google cultural cognition is a good buzz phrase. Cultural cognition. Just basic social bias stuff, and there is some research on that it exists. Very limited research on how to counter it still. But I think if anyone was awake during 2020, you saw it in action. Whatever side of whatever issue you're on, you know that there's another side that is just diametrically opposed, and you know that they can't both be right.
Yeah.
Right. It's like we've probably seen the meme of the one guy walks up and says, "Oh, it's a 6," sees a 6 on the floor, and then the other person walks up and says, "No, that's a 9." And I think the meme is intended to get us to agree they could both be right.
It's based on perspective.
Yeah, sure. And so that's step one. Step one is acknowledge the other side has a point of view. Yes. Step two is maybe we should figure out which one of them's actually right. Because like if they're waiting for the bus or they're waiting for the train and they're looking for platform number 6, one of those chaps is going to miss his train.
Yes.
Right. There might be a right answer. And fighting about it won't get you there.
No, it won't. And I think that this kind of ties back into the honesty issue. And I think this is where, particularly with flat earthers, particularly now with the evolution of flat earth, you really get into the question of honesty. Because I think there's going to be only so much you can do with a person, sort of meeting of the minds and then trying to determine what is actually fact or what is true. There's only so far you can go if the person is dishonest. If the person isn't willing to accept what you have to say, anything that you have to say, you can't, as they say, you can lead a horse to water. Because that's something else that I've been thinking about. Is I've heard that there is some research out there that says that when you have someone who's skeptical of science, actually just teaching them the science gets you nowhere.
No, it does not. And in fact, it can rebound. A lot of studies on the rebound effect. And you said some things there that are also red flags, and that you've already called them out earlier. So I don't want to criticize you for it. Maybe just we need help reminding each other that dishonesty is, it's hard to pin down, because something that I have really learned in my research into flat Earth, the thing that I learned more than anything else, is that the human mind can lie to itself, and convincingly lie to itself, to the point where you are absolutely positive that you are correct.
Oh yeah.
But at the same time, there's another part of your brain over here that is chuckling because it just totally fooled you. And there's part of your brain that knows that you're lying, and there's another part of your brain that's absolutely convinced you're telling the truth.
Yeah.
So
Mandela effect is a prime example of that. People remembering, he says, Luke, I am your father. No, actually he doesn't. And that's demonstrably true. So yeah, when I say dishonesty, I don't want to imply that I think that these folks, that if they are being dishonest, they're being dishonest in a purposeful negative way. And yeah, maybe that is a microaggression. That is something that I try to pay attention to in how I address things. But that's not my intention. That my intention is not to say that if someone is being dishonest, they're doing so in a negative way.
Right. But it is a trouble, because this is the internet, right? So I think we have to recognize, I think on all sides, we need to recognize that there are dishonest players on the board.
Yeah.
We don't know who they are necessarily. So we're all going to have to judge. And Alan is calling it out here. That's what it comes down to, I think, is we see a bunch of players on the board. We know that some of them are dishonest, but we don't know which. How do we decide? And the way humans decide that is basically tribal. We identify who is our side and who is the opposing side. And that's what we do.
The thing is, and this is the question that I've been kind of rattling around in my head, is like Rachel did a couple of videos where people were calling her Poe and going off, and I'm like, is that really? Let's assume that she is. Let's assume that she is actually disingenuous and dishonest, and she's doing all this for the clicks and all that kind of good stuff. Does that actually matter in the grand scheme of what we would like to do? Our goal is to educate. Our goal is to get people to look at this in an objective way. Now, and in doing so, with someone who is disingenuous, because is it that we are trying to get her to switch sides, or are we trying to get anyone who's witnessing this to look at this objectively? So I don't know how much it adds to the conversation to determine whether or not these people are actually disingenuous. But I think that the part of the conversation that's necessary is, how do you sort of combat disingenuous arguments? I guess that would be where I would go.
I think that is fair. And I think also there's you see a similar point of view expressed often. Don't waste your time. Don't waste your time with someone who's not genuine. Or perhaps a better way of looking at it is, don't waste your time with someone who you cannot change their mind. Someone who's not being genuine, clearly you're not going to change their mind. The only thing you can do with them is out them. Although I did see that once. I did see FTFE had a live debate with somebody and managed to out him as a Poe.
I think we've gotten to the point that we can pretty much out Thompson as a Poe as well. But
who?
Nathan Thompson?
Nathan Thompson? You think he's a Poe?
Yeah, actually, I do. I do.
Wow. Okay. We should talk about that. That's just an interesting tangent. I wouldn't have pegged him as a Poe.
Yeah.
I'm usually the first one to go, I bet, yeah, I think he's a Poe. But no, I believed him. He cries on camera so well.
I have a lot of opinions on Nathan Thompson, but I just want to say one thing. Just kind of going back, Rachie, if you actually do watch this, I want to unequivocally state I do not think you are a Poe. I was just using that as an example. I do not think. I think you are a genuine person. I think your interest is genuine. I just wanted to make that absolutely clear. So.
Yes, thank you. I agree. I thought that was clear, but thank you for calling that out, because some people aren't going to necessarily hear your words the same way that you meant them.
Yeah.
And if I've got a message, for the community on both sides, that's it. That's when you say a thing, the other person doesn't hear the same thing that you said. We all take what we hear and filter it through our own experience. And when one person says, gravity's not a force or something, that means different things to different people. Let's just all just slow it down, calm down, and just ask, hey, what did you mean by that? Did you mean that? That's the way I'm taking this. I'm taking your words to mean this. Is that what you meant? And maybe we can all just come to an understanding,
I agree. And that's one of the things that I think I actually asked you about it in that, definitions. How are we defining things? Because we can't move forward if we don't have a commonality of language. If we don't believe, if I say wait and you say wait and we are not thinking of the same thing, then whatever conversation we have is going to be fairly meaningless.
Yeah.
Or at least unproductive. So
absolutely.
Yeah.
And so I will try not to use that word.
Yeah, I still, that's another conversation I would really like to have with you at some point. I don't know if that's I have thoughts on whether or not that's an appropriate strategy to use. I won't say it's right or wrong. I have my own questions about that.
I'm trying it. It's an experiment. I mean, it's my own personal experiment. And can I reach across the aisle to the other team? That's what I'm trying to do right now is just like in Little League, right? You can fight. You're fighting for every run on the play field, and then win every point on the play field for your Europeans. But when the game's over, we shake hands, right? We don't walk home hating each other. So that's what I'm trying to do. Let's reach across the aisle. Let's shake hands. And you know what? I want to do real science. And a lot of you say you want to do real science. So we have the same goals. We should be working together on this thing, not fighting each other. And if anyone is willing to work together, I'm telling you, we can do it, because we can science the heck out of this thing.
Yeah.
And all the answers can be found. They absolutely can be found. Or, lots and lots of answers can be found.
I'm fully on board with that. The other thing that I think is important to know and to try to accept is it's okay to be wrong. To be wrong about something is not an indication of your own character. If you are wrong, that does not reflect poorly on you as a person. It just means that you were wrong about something, and you can be right about it when you figure out what the truth of the matter actually is. And so I know I have a problem with that. Whenever someone has shown me to be wrong, yeah, I kick myself. I get frustrated because I think to myself, hey, I should know that. But, and I try to tell myself, no, this is a learning experience. This is how learning happens. You have to be wrong in order to learn. So,
yeah, absolutely. Good words. Embrace it. Embrace being wrong. Rachie put out a video on the balloon. Did you see the balloon going backwards?
No, I watched that one.
She asked me about it before she published the video, and I guessed wrong. What it is she got a balloon, and then she just takes a piece of paper, and I'm going to be in front of the camera here, and she fans the balloon.
Okay.
Like this. And you'd think that the fanning action would push the air, and that would push the balloon away from the fan.
makes the air less dense. It drops the pressure. Yeah, it's like a wing.
Bernoulli's principle, though, she's mostly moving that air side to side. And so the lower pressure sucks the balloon towards the fan, and it's completely counterintuitive, but amazing and incredible. She made a discovery, you know, and it's really cool. And so, yeah, super applause for that kind of thing. Yeah, and I'm right here emphasizing that I was wrong. I thought that it would probably blow the balloon away. But when I saw it, I was like, oh, it didn't. I guessed wrong. And yeah, we can figure out why, right?
Mm-hmm.
That's
that is the beauty of science, is finding things you don't expect. Because then once you find something, once you see something you don't expect, then you get to have the fun of trying to figure out why it did what it actually, did, why it did what you didn't expect. So,
yeah, I like to emphasize that to the skeptics, the science skeptics who think that science is just about memorizing facts out of a book. That's all we do, is we memorize facts from the book. No. Actually, the reason science exists is because our intuition is imperfect. The way we expect things are going to play out does not always play out that way. If it did, we would have no purpose for science. We would all just know everything already. But, sometimes things don't turn out the way you expect. And so we go through, procedures to try to figure out what really is happening. And that's what science is. It's not memorizing a bunch of facts.
No, it's actively participating and trying to figure out why a set of observations for astronomers. And I noticed you had a video on the scientific method. And the scientific method is problematic in and upon itself, because particularly with Sleeping Warrior's understanding of it, because they'll use a scientific method to basically tell me that astronomy is not a science, because my research is primarily observational in nature, but that's another story entirely. But another subject or conversation entirely. But I think where I was going with this was that, yes, science is a process of actively investigating what you would not have expected to have happen. And I have banged my head up against that wall numerous times, where I'm trying to explain why my data is showing what it's showing, and I just can't figure it out, and I just keep kind of banging my head up against that wall until something gives.
Right. Yeah, that's right. And that's the key, is if it was what you expected, there'd be no point of doing it.
Yeah. Right.
So if you expect that when you add salt to water, an egg is going to rise for whatever reason, because the sky is blue. If you think it's because the sky is blue, and you do it during the day with a nice blue sky, you just confirmed your expectation is all you did. You need to then do it in a cloudy day, and then do it again at nighttime, and then you're going to discover it has nothing to do with the blue sky, right? And that's right. You got to you can't just confirmation bias all the time. You've got to
identify what your variables are, what sort of physical processes or what factors may affect the what's going on, and so forth. Yeah.
All right. Well, it's been great. Why don't you plug? Do you have some content on your channel yet? Actually, you want to plug?
I have. It's Rob Parks. You can search me on. YouTube under Rob Parks. I think. Can I comment on this?
Can you type in the comments? Do you have access to the comments?
I don't know if I can leave comments. I think I can put it in private chat, but
you only have private chat?
Private chat, and I can see comments. I can't.
Down at the bottom, it doesn't have post a comment?
Nope.
All right, put it in private chat. I'll copy it.
You've got my name there. When I start, so right now, the only content that's up is lectures that I've given due to the current situation because of remote distancing. There are some times when I have had to disseminate lectures, but I couldn't do it through my normal resources, so I did it through YouTube. So if you're interested in astronomy lectures at the collegiate level, then introductory collegiate level, then yeah, please go by and look at my stuff. Eventually, my shtick is going to be Rob World, where I will be doing. The idea is that I will be focusing like a 15-minute video on specific astrophysical phenomenon, like for example, the Doppler effect. What is the Doppler effect? How can you see it? That sort of thing. Kepler's laws. I'll talk about that. What I'm struggling with right now is the exact formatting and really how I want to. I mean, do I want to approach this in a these are the facts, or this is what we know, or do I want to approach it more in an investigative sort of way? And if so, how to do that? Really, I'm probably overthinking it, and I probably just need to do it and just see what comes out at the other end. But
do it and see what the fans like, perhaps. If you want to tie it into, the skeptics concept, the one thing I would suggest is to show the beauty and the glory of the night sky. As you will have access to your own images that are so much better than what most of us can do. I would highlight that. I would highlight how wonderful it really is when you focus your telescope to see things, and that you are a human person that's doing it yourself. You are not the man. You are not the institution. You are a real human being who loves this material and loves to do it and can go out and share it with you.
Yeah.
Right.
I would. That is. I do want to. One of the things that I want to do. I don't know if it's part of that series or what have you, but I would like to highlight the work that's being done at our observatory, and show those images of the night sky and explain why I fell in love with this to begin with, because I have known that I wanted to be an astronomer since reading about Vera Rubin in the 7th grade. Now I have gone away from cosmology, and I will be the first to admit, I admit this to AB Science, cosmology, the math, it's a little higher than my head. So I moved away from studying cosmology specifically, but yeah, dark matter one of the emails that we've exchanged dark matter. Dark matter was actually my first introduction into astronomy as a science, and that's what hooked me. So
yeah, that's definitely beyond my my comfort level as well. But I follow it. I'm looking very, very much looking forward to the professional scientists producing some results that will be very interesting. But yeah, going out and taking pictures of stars and nebulas and planets and sunspots and all kinds of wonderful things that you can see and share it with people. I think just doing that will have more impact than any debunker ever could do, because they see these images of out of focus, weirdly shimmering lights in the sky, and they hear the voiceover of someone telling them that's what it really looks like. It'd be kind of cool to see, oh, look what it actually does look like. And no, I'm not someone who's fooling you. Here, take a look at my telescope. Take a look at me, and here's my assistant, and this is a grad student, and look at the telescope they've got, and this is the research they're doing, and it's not just made up, read it in a book, fake CGI images, right? Yeah.
Yeah, exactly. Yeah, I definitely said I definitely would like to host that. The again, one of the sort of mental stumbling blocks that I just need to get over is, when I sit there and I think about, all right, well, what if I, just had streamed myself taking images off the telescope? Uh, they're going to say, "Oh, this is fake. You're just, you're using a computer to do it." And I'm like, yeah, I should just get over myself and just do it anyway. So.
Yeah. You probably use some regular old optical stuff though, don't you?
Well,
You
so
graduated to the point where you don't even use plain optical telescopes anymore.
Well, no, we use so we have a 0.8 meter or 32-inch telescope with a digital CCD camera. I guess that's kind of redundant, but digital camera or CCD camera.
Yeah.
So we don't use eyepieces anymore. We take digital photographs of space. So
Right.
in that sense, that's kind of where I was expecting kind of the pushback of people being like, "Oh, that's not real," because I'm not seeing it with my eye. It's only taking digital photographs of it. So, but like I said, I need to get over that and just do it.
All right. Cool. Very cool. All right. Thanks for talking to me.
What is your first name?
Oh, you can call me Matt.
Matt. Okay.
Yeah, I'm a little bit cagey. When I first started, I was super cagey. I wouldn't show my face or anything. Because I do teach at a major university, and I don't want that to be part of this. That is not why I'm here, and I don't want somebody who's belligerent to come to my class, right?
Yeah,
I don't want that. I don't want to come into my home or whatever.
I've probably already, because my YouTube channel was my last name. I've probably already outed myself, and I'm worried about that to a certain extent. So I get it.
Yeah, but I've found that for the most part, the belligerence has to be mutual. If you don't want to fight, you don't have to fight. And I have found, at least, so I'm very small. My channel is itty bitty, so maybe that's all going to change if I ever grow. But so far, people have been mostly on board with it. I remind them once in a while. Somebody comes in when they're new. They come in and they start the trash talk, and hey, we don't do trash talk.
Mhm.
Edit that, or I'm going to remove it. And if they only want to trash talk, they don't come back. And other people actually want to discuss the topic, then you're welcome to. You're welcome to discuss it, even if you don't listen. You're welcome to just come and say your piece. That's all right.
Sorry. I just want to I sent you in private chat the link to my YouTube channel.
Oh, I see it.
Yeah, because I noticed that Jeza mentioning there are a lot of us. So yeah.
Okay. Yeah, there is, and I'll put it on the banner. I got to get better at this if I'm going to do this more. Yeah. So there you go. That's that. I mean, you read that off the screen, but it's in the chat, right? So you see that on the screen, go open the chat, which you can do, and then that should be there. All right.
Are you planning on doing this with other people, creators, non-creators, that sort of thing?
Absolutely. In fact, Alan, who's in our chat right now, is a new person that I have just met today on YouTube, and I would very much like to have Alan come on soon and ask his questions. Alan is one of the people who have a great many questions because he has seen these videos. Like they're talking in the content and comments, I can see that they're talking a lot about like green screens on the ISS and that kind of thing. I've seen those videos. Yeah. I could totally see where I could believe in that. I could see where they're coming from with those videos. it's worth a talk. And we can talk about that stuff. Ultimately, you know, I'm pretty biased, so you're gonna have to keep kicking me, Alan, to remind me that I'm biased. You know, I used to work at NASA. So
Oh, nice.
yeah, when I was in grad school, I did grad school at NASA. So yeah, I'm a fanboy of NASA. So keep me honest. But yeah, it's important to me that I am honest and objective. So
yeah, the only thing I can't claim that I work for NASA. The only thing I can claim is that some of the funding for my research has come from NASA.
yeah, all right, yeah. So you're a show for sure.
So
You're still a show.
yeah, but if you ever want to have me back on, that would be an honor. I would love to if you wanted to just chat the two of us, or if you wanted to have if there's someone who had more of astronomical questions and you wanted to help fielding those, I would very much like to be a part of that.
Absolutely. Yeah, sounds good. Thanks for coming on.
Thank you.
It's really great talking to you.
Yep.
And I hope everybody that if you watch this whole thing, you got to see what it's like when science nerds fight. So yeah, it happens, right? We aren't all just reading off the page. We do have to be convinced of things.
Yes.
And that's how we go. And we can do it respectfully. And we can have fun doing it. And that's where it's the good stuff.
I agree. All right. Till next time.
All right. Till next time.
See you all.
See you all.